Okay, so in the last video lecture that we had, we talked about a couple of the definitions that would be required to solve this model, some of the economics, some of the equilibrium concepts we went over. So now it's time to actually solve the model out. So we will be finding the solution to the Solow model. We'll do it mathematically, then we'll do it graphically, and that will probably wrap up this video, and then I'll post another video rather shortly that's going to cover some of the stuff to sort of help sand off some rough edges with the model. So what we need is another definition. A steady state equilibrium occurs when all variables are growing at a constant rate. Means today's value is equal to tomorrow's value, and so on and so forth. So what does that mean for the Solow model? Well, what it means is we are going to want to find a way to solve this model where all of the dynamic variables, so we're looking at capital, we're looking at consumption, investment, which is really defined by the flow of capital over time, output. We want all of those things to be in a steady state. We want them to be constant over time. So if they can be constant, right, so think of them as just moving along a flat line. If there is some sort of an economic shock that occurs that forces it out of that constant state, it'll eventually converge back to where it was, and we can see how the economy responds. That's going to be the point of trying to find the steady state in these types of models. All right, so in a steady state, we can say that capital tomorrow is equal to capital today is equal to K with a little SS subscript, meaning steady state, or K with a little star over it. Right? Whether you use this or this, I'll know what you're doing. So if you choose to use either one on any homework, exams, etc., I'll know what's going on, so, because, well, they just kind of say the same thing. Right, so this SS subscript right here means steady state. Now, if we can solve for steady state capital, we'll get output in the steady state, but we'll also get investment and thanks to Walras' law, we can get steady state consumption too. Why? Well, if you remember, we have this as the resource constraint within the economy. Output is equal to consumption plus investment. It can't be split any other way. So if we can get steady state output, or YSS, we can get steady state investment, which is ISS, then we can infer, thanks to this constraint right here, what steady state consumption will be. So let's just get down to it, shall we? So this is how we're actually going to put the model into a steady state. I did a lowercase a last time, so I will do a lowercase a this time as well. Alright, so with these three equations here, if you remember from the last time we did a little bit of math, I can take this equation and this equation, substitute them in for output and investment accordingly, which gives me the following. So this should hopefully look kind of familiar. You will likely see this constraint ad nauseum by the end of this semester. But this is what we have when we're not in the steady state. When we are in the steady state, what we do is we replace all t and t plus 1 subscripts. And then SS. So what we get is ASS, and there's a wordy nerd, times KSS to the alpha, so this is output in its steady state, equals steady state consumption, CSS, plus capital in the steady state, KSS, minus 1 minus delta. There's no SS subscript for this delta here because it's a time invariant parameter in this model. We multiply this 1 minus delta times KT, so here it's 1 minus delta times KSS. Right, so if you look, every single subscript that I've got here has just been turned into an SS for steady state. And then here, we need to recall something. Savings is a constant fraction of output. Right, so savings is equal to S times YT, where S right here is some constant fraction of output. Right, well, we remember that was equal to investment. So if S, which is between 0 and 1, is equal to investment, then one minus that fraction, 1 minus S times YT is going to be equal to consumption. So what we can do with that, this little bit of information here, I can substitute out the CSS So I have everything in terms of capital. Oops. Made a oopsie. Alright, so I do 1 minus s times yt. Now if you remember, yt is equal to at times kt to the alpha. So in the steady state, output here is equal to ass times kss to the alpha. And I multiply it by 1 minus s because 1 minus the fraction that's saved is the fraction that's consumed. So what I have now is something that is much more workable. I'm going to get this right here. So this is consumption. This is investment. Consumption plus investment equals output. So now you might think, oh, hey, cool, guess what? Everything's already in the steady state. We're done. We don't have anything else to do. Well, not so fast. Because these are still in terms of the endogenous variables. They don't tell us anything. You want them to be in terms of A, this ASS here, alpha, capital share of output, delta, the rate of depreciation, and S, the savings rate. So how do we do that? Well, notice the only endogenous variable that I have I'll go ahead and label this with a star. So I can say equation star. Only endogenous variable in there is capital. So if we solve it for steady state capital, we have the solution for KSS in terms of, you guessed it, only the exogenous parameters slash variables. Right, because there's no CSS, there's no ISS, there's no YSS. So the only endogenous variable that we have in here is capital. So if we can solve for KSS, then boom, we automatically have the solution for steady state capital in the form that we want it to be in. So get a good look at that for a second. I'm only giving you a second because you can always just push pause. Now I'm going to erase it, and we will begin solving this thing for KSS. So I'm going to write out this guy over here. Then I'm going to erase this. We can use a different color marker too now. Let's see what we have that's cool. Oh, light blue. Like, ooh, piece of candy. So let's solve this out. Well, the first thing I'm going to do keep this part and this part the same, but I'm going to look at this KSS minus 1 minus delta times KSS. All right, well, I'm going to add KSS still, all right, but minus 1 times KSS, what is that? Well, it's minus steady state capital, all right, and then minus negative delta times KSS, well, negative times a negative is a positive, so this is what I get. So I get steady state output equals steady state consumption, which can be re-expressed as 1 minus S times steady state output, plus steady state capital minus steady state capital plus delta times steady state capital. Well, I've got plus KSS minus KSS. So these two guys just go to 0. Now, this is what I end up with. ASS times KSS to the alpha equals 1 minus S times ASS times KSS to the alpha plus delta times KSS. Now, I'm going to go ahead and expand what's going on in here. So again, the left-hand side of the equation remains the same. I'm going to get ASS times KSS to the alpha minus S times ASS times KSS power of alpha plus delta times KSS, like that. Right, well, now I'm going to subtract both of these from the left-hand side. So I'm going to get ASS times KSS to the alpha minus ASS times KSS to the alpha. All right, minus negative S times ASS KSS to the alpha is going to be plus S times ASS KSS to the alpha equals delta times KSS. Right, well, these will go to 0, so now I just have S times ASS, KSS to the alpha, equals delta times KSS. Okay. Not bad. What else can we do? Well, let's divide both sides by KSS. Right, what am I going to get? Well, I'm going to get S times ASS times KSS to the alpha minus 1. Okay, because this right here, KSS to the alpha minus 1, is the same as KSS to the alpha divided by KSS. Right, but it's easier to write alpha minus 1 than it is this to the alpha over KSS. It's just quicker and easier. Right, and that's going to be equal to delta. Right, because the delta still stays over here, but KSS over KSS is just 1, so it's delta times 1. All right, and then I want to divide both sides by S. So now I have ASS times KSS to the alpha minus 1 equals delta over S. Right, well, now I'm going to divide by ASS. Like that. So what I end up with is KSS to the alpha minus 1 equals delta over S times ASS. Like that. But what I want to do, because remember, this alpha minus 1, it's great. Alpha is greater than 0, less than 1. So alpha minus 1 would be negative. All right, so I've got a negative exponent here. But for reasons we'll see in a moment, a positive exponent would be better. How do I do that? Well, if I invert both sides. If I raise both sides of this equation, what I would get, if I raise both of these to the power of negative 1, flips them, so now I get KSS the 1 minus alpha equals S times ASS over delta. Now there's one last thing I have to do. Raise each exponent to the power of 1 over 1 minus alpha. Keep trying to write a capital A there. My mistake, no fault or problem of yours. So this is the Solow model solution for steady state capital. It's S times A over delta to the power of 1 over 1 minus alpha. So right now you're probably going, what in the ever-loving hell is this guy trying to pull? What is he showing us aside from a lot of math? Well, let's talk about it. I'm going to erase all this stuff because I need board space. So give me just a moment to erase this stuff. I'm going to put this up over here. We can talk about what it means, and we can go from there. So, in the steady state, capital is equal to S times A over delta, all to the power of 1 over 1 minus alpha. You remember S, the savings rate. A is the source of technology shocks. Delta is depreciation, or the rate at which capital falls apart. Right? These two are good. If either the savings rate or the source of technology shocks increase, meaning if people decide to save more, or if we get new technology shocks in the economy, positive technology shocks, because if A increases, technology goes up. So if we can use more technology, and we can use that technology to produce more efficiently, meaning we can ultimately produce more with less. Right? We can use capital more efficiently, then steady state capital will increase. Delta, on the other hand, is bad. Delta goes up, steady state capital falls. Because if capital's falling apart faster, right, the steady state level of capital will decrease a little bit and be lower. Because we need to put more capital in order to be able to maintain a nice steady state. But if we're saving S at some rate that is not sufficient to maintain where steady state capital was, we'll get into what this means in a minute, then the increase in depreciation will drop steady state capital, and steady state capital will be lower. So this is how we express steady state capital in the Solow model. And again, the technology shocks, I'll explain those when we draw out what the Solow model looks like graphically. But we're not quite there yet, because we need to finish up a few more things. Right, because we still need steady state output. If you remember, steady state output is equal to A times K to the alpha. Right, well now I know what K is. I plug this in for K. Right, because remember I was saying we want all this stuff to be in terms of the exogenous variables like A and the exogenous parameters S, delta, and alpha. Right, there's no C here, there's no Y here, there's no I here. Right, it's only the exogenous stuff. So I take this and plug it into KSS. Keep trying to do a capital A, and I don't know why. So I just plug this guy in here, and what it gives me is this. Steady state output is equal to A right, because A was right here, times steady state capital, KSS, which is equal to S times A over delta. Right, but for production, capital is raised to the power of alpha. So if I have something to the power of 1 over 1 minus alpha raised to the power of alpha, what I get is alpha over 1 minus alpha. And this is the formula, or the mathematical expression, we'll say, of steady state output in the Solow model. This steady state capital will never look any different than this. Steady state output will never look any different than this. Which is probably a good thing, probably making you feel pretty happy, right? Because when you have to do this on an exam, well, you're going to know exactly what steady state capital is. You're going to know exactly what steady state output is because they're right here. They're not going to change. So, that said, I'm going to erase some of this stuff and add steady state capital, or steady state output, I mean. Right here. And there is steady state output. And from these two, we can get either steady state consumption or steady state investment. Let's find steady state investment. You remember, steady state investment, right, would be equal to steady state savings, which is just S times Y, S times YSS, savings times steady state output. Well, I already know what steady state output is. So steady state investment is just the constant fraction S of savings that we save every single period times steady state output. So it's going to be S times ASS times S times A over delta to the power of alpha over 1 minus alpha. It's a steady state investment. Want to take a wild guess what steady state consumption is going to be? I'm going to give you a hint. It's probably 1 minus S times this. Steady state investment, steady state consumption, steady state output, steady state capital. We always want to start by solving for steady state capital. Then we're going to want to plug steady state capital into the production function to get steady state output. After that, we can back out steady state consumption, and steady state investment. And that is how we solve the steady state, or how we solve the Solow model for the steady state endogenous variables. The next video, I know I kind of lied, I said it was going to happen in this video, it's going to happen in the next video. The next video is going to graph this stuff out, draw what it looks like, show you what it looks like, and we can go from there. So, until next time, peace.